So the bottle on the left, that has a lot of nitrogen dioxide in it, and then the bottle's sealed. And nitrogen dioxide has an orangey, brownish color to it. Now, if the reaction happens the way we've written it there on the right, you would expect that the nitrogen dioxide would react until it completely turns into dinitrogen tetroxide. Now, dinitrogen tetroxide is colorless. So what you would expect to happen is you'd go from a bottle that has kind of a brownish orange gas in it, and then it would eventually become colorless. You look on the bottle on the right, that's not the case. After you wait a certain period of time, the color diminishes, but it stops changing. That means there is still some nitrogen dioxide in there. And that means the way I've written the chemical equation isn't a sufficient way to look at it. So instead of using that single arrow, we're going to throw in a double arrow, which is commonly known as an equilibrium arrow. And what this shows is the reaction goes not only from left to right, but now it goes from right to left. It's common to take a quick look at this at the end of chemical kinetics when you're discussing reaction mechanisms. But now this is a major focus of a lot of the rest of general chemistry too, looking at what's referred to as reversible reactions. Now, the reason why the bottle on the right still has some color to it is we've attained something called chemical equilibrium. And it means the rate of the forward reaction, the nitrogen dioxide to dinitrogen tetroxide, is equal to the rate of the reverse reaction, which is the dinitrogen tetroxide forming nitrogen dioxide. And when those two rates are equal, then we're at this position of chemical equilibrium. Now, nothing is said about how long this takes. That's in the realm of kinetics. I've got the word dynamic in parentheses at the end, and the reason for that is it doesn't mean that everything stops. So you still have the forward reaction happening and the reverse reaction happening. It's just that those rates are equal to each other. Depending upon where you live, you may not have had a lot of experience with smog. This is a picture from Los Angeles in the early 1990s. If you look in the center area, that's downtown. You can see in the foreground the East Los Angeles River, and in the background you can see the Hollywood Hills. And the way that you can determine how much gas is in there and what type of gas it is, you can take a sample out and then examine it using a colorimetric analysis. In other words, using the color to tell you what's in it. It's not quite the same thing, but if you think back to Chem 1, oftentimes you do a spectrophotometry experiment where you use something called Beer's Law, where color tells you concentration. And a similar idea here. So let's look at some data. What we have in those first two columns are initial concentrations of the two chemical species, and then the other two columns are what the concentrations are at equilibrium. And we're going to do a bunch of different possibilities, in fact 5 different cases. And I've got a column there on the right, and I'm not going to say what that's for yet. So we'll take our container and fill it completely with nitrogen dioxide and then cap it. And we wait long enough for it to come to equilibrium. And we determine at equilibrium that these are the concentrations of the gases. Now, in case you're worried, if you're going, well, wait a minute, shouldn't we be doing pressure since they're gases? You can do concentration for gases. Remember the square brackets, moles per liter. There's no reason why you can't do that with a gas. How many moles of gas do you have? What's the size of the container? Moles per liter. All right, now here are our new concentration values at equilibrium. And then I wave my magic math wand and ta-da! I'm not going to tell you how I got that just yet. If you look at a graph over time, notice how at the beginning, the far left, you start with a lot of dinitrogen tetroxide and no nitrogen dioxide. And then over time, look what happens to the graph. Look how it's horizontal for both. What does it mean slope-wise when a plot goes horizontal? The slope is 0. That means there's no net change. So if you're looking at a graph like this and you're trying to figure out where's equilibrium, it's on the right side when the slopes go horizontal. Well, let's look at another setup. And we'll start by putting nothing but dinitrogen tetroxide in the container. Now, if this had been Chem 1, and if I had said we're going to take a container and fill it with nothing but product, what do you expect to happen? Well, your response would have been nothing. It's a product. Reactants go to products. Duh. But now we're looking at equilibrium. So we can have the reverse reaction happen. Now the concentrations are about the same when we finish. And whatever I did mathematically to those equilibrium values in trial 1, well, they're the same number, so you should get the same number there in the far right column. That's no shock. So we look at a graph. We start with all nitrogen dioxide and no dinitrogen tetroxide, and we allow the reaction to occur over time. Equilibrium, no net change. No net change means slope of 0, horizontal lines. There's our equilibrium. Another trial. And, okay, it looks like trial 1, but I did adjust the nitrogen dioxide initial concentration. And then we wait. And this is what we get at equilibrium. Those equilibrium numbers are completely different than what we see in trials 1 and 2, and yet, if we do the same mathematical operation, we get a number in the right column that's very similar to the other two. Let's try it again. Fill it with all of the product. And we wait for equilibrium. And this is what we see. Completely different numbers. And yet, we get a number that's very similar to the other three. And then, we'll do something different. We'll put a little bit of everything in it. Now, in Chem 1, when we studied chemical reactions, if we would have done this, it would have been, well, who cares how much product? We'd ignore it. So you go, oh, well, you should have, well, but you can't have the same equilibrium concentrations. You start, okay, so it gets very confusing. So it's the numbers. And if we manipulate them the same way, we get a very similar number. So what we need to do is find a way to do a mathematical analysis on equilibrium values that will let us determine when we're at equilibrium. That's the next thing we have to figure out. What did I do mathematically to those two columns to get the third column?